Welcome back. It's been a long time since we've done a video. So today we're looking at day 66. We're going to be doing some integral approximations here, specifically left and right Riemann sums. So Riemann sums, there's going to be a few different ways that we do these. On the test, oftentimes you have to do them in table form, is the most common. But we'll look at table form tomorrow, and you'll find table form a lot nicer. Okay? But for today, we're going to take a look at doing them through the graph to figure out what exactly we're doing. We need to see it in a graph first, so it makes sense on how to do it from a table. So let's talk about what a Riemann sum is, left and right. So I'm just going to sketch a graph here. So here comes my function. So here's my function f of x. Okay. And let's call it a here and b here. What I want to do is I want to approximate the integral from a to b of f of x dx. So I want to get an approximate value for the area between the curve and the x-axis from a to b. Okay. Now this is a curved function, right? So I can't do the work that we were doing today in class where I just, oh, it's a triangle. I know the formula for the area of a triangle or a rectangle or a semicircle or anything like that. Right? We just have a curved function here. So what I want to do is I want to figure out a way that I can estimate the area under this curve here. Okay. Now when we're starting to learn these left and right Riemann sums, I don't want you to get bogged down in the fact that, like, hey, this isn't the best way to guess the area under the curve. Okay? Because when we do this early on, our answers aren't going to be very, very good, to be honest. Okay? But that's okay. It's a learning opportunity, and it's going to help us develop where we got an actual integral from, like how we can actually calculate the exact area under the curve. So here's my approximation. I want to approximate the integral from a to b of f of x dx, and here's what I'm going to say. I'm going to say approximate this using n equals 4 rectangles with a left Riemann sum. Okay. A Riemann sum is simply, we turn the area underneath the curve, or close to it, we just turn it into rectangles. Okay? All we're going to do is turn this into 4 rectangles because it's really easy to calculate the area of a rectangle. Okay? Now, I said at the beginning we have left Riemann sums and right Riemann sums. So, what's the difference there? Well, it depends on which side of the rectangle we're using for our height. So the first thing I want to do is I want to chop up this area between A and B into 4 equal rectangles. So here's what I'm going to do. I'm going to use a different color here. So I want 4 equal rectangles. I know one rectangle we're going to have at the beginning and the end. So what I do for 4 equal ones, I draw one right the best I can in the middle, and then cut both of those in half. Okay? Now you may say, hey, those aren't rectangles, right? They're not rectangles yet. Okay? So as we see here, I have 4 equally spaced, or I tried to equally space, right? There are 4 equal spaces down here. Oh, I'm really bad at that. Okay. They're not rectangles yet, but I'm going to turn them into rectangles. Those are 4 equal sides to a rectangle. Now, depending on if I'm doing a left Riemann sum or a right Riemann sum, depends on where I make the top of this rectangle, right? The base of the rectangle is the x-axis, and the sides are those red lines. But to figure out where to make the top, I need to follow whether I'm doing a left or a right Riemann sum. So taking a look at this first rectangle, this rectangle right here, I want it to be a left Riemann sum, right? So this one is on the left, this one is on the right. So I want to use the left, right, where that side hits the function f of x. I want to use that to create my height of my rectangle. That'll be right. I'm going to cut it right there. And what I'm going to do is I'm going to find the area of that rectangle. Then for the next rectangle, again, now this one is left and this one is right. So I want to use the left to cut the rectangle. And again, I want to use the left to cut the rectangle. And lastly, I'm going to use the left to cut the rectangle. And all I'm going to do is add up the areas of those 4 rectangles. That's it. Right? We can find the area of a rectangle very easily. It's just the base times the height, right? Or the length times the width. I like base and height when I'm looking at it like this, right? And that colored in red area gives me an approximation of the area underneath the curve. Now, when you look at this particular approximation, we should be able to determine, right, the area of those 4 red rectangles. How is that going to compare to the actual integral from a to b of f of x dx? Right? Is this an under approximation or over approximation? Well, it's pretty obvious to see by looking at this that this is definitely going to be an under approximation, right? All of these white areas here, right here, right here, right here, right here, all of those white spaces, they kind of look like triangles, right? All of those white spaces would actually be part of the actual integral from a to b of f of x dx. But we're not counting them because we just don't have a very exact method for it. Okay? So right now, if we do a left Riemann sum here, we are going to get an under approximation. So like if I get an answer of 10, I know that that number is a little bit too low. Maybe it's actually like 12 or 13 or something like that. Okay? A right Riemann sum, I'm just going to erase what I have here. A right Riemann sum is the same idea with if I was doing a right Riemann sum. And in your notes, you can draw this in a separate one or just kind of observe. If we do a right Riemann sum here instead of a left Riemann sum, I would use the right part of the right side to make my top. So a right Riemann sum, right? We'll change this to a right Riemann sum. That would look like this. And then if I color it in, it would look like this. Now if I add up the areas of those 4 rectangles, I get an approximation for the area under the curve. Now, I'm going to ask you the same question I asked last time. If I did a right Riemann sum here, am I going to have an under approximation or an over approximation? Well, again, it should be pretty obvious to see here that I colored in places. These 4 places that I colored in, right up here, here, here. Those pieces of the rectangle actually go above the curve, right? They wouldn't be included in my integral from a to b of f of x dx. So I'm counting too much. I'm covering all the area that's supposed to be there, but I'm counting too much. So this would be an over approximation. Okay? So a right Riemann sum in this case is going to end up being an over approximation. So maybe I do this, I count up the area of all four of those rectangles, and I get, let's say I get 20. Well, I know that's too big of a number. Maybe the actual integral is equal to 17 or 15 or something like that, right? So in this case, my right Riemann sum is going to be an over approximation. What I want you to think about, I'm not going to talk about it in this video, but I want you to start thinking about this. Will a left Riemann sum always be an under approximation? Will a right Riemann sum always be an over approximation? Or does it depend on what f is doing? I want you to think about that a little bit. Okay, so here's what I'm going to do. We're going to do one problem here, and we're going to figure this thing out, and we're going to do it with an actual function. Okay, so what I want you to do is consider this. I want you to approximate the integral from 0 to 3 of x squared plus 1 dx using a let's do a left Riemann sum with n equals 3 equal subdivisions. That's just a fancy way of saying I want 3 equal rectangles there. Okay, so my function here is x squared plus 1. And I want to do a left Riemann sum from 0 to 3, right, with 3 equal subdivisions. So what I'm going to do first is I'm going to sketch a graph of this function, and I'm going to sketch it, I need to sketch it from 0 all the way to 3. Now what I'm going to do here, I hope this doesn't mess you up, okay? On my graph paper here, I'm going to go every 2 spaces as 1 on the x. So I'm going to call, just to give me a little bit more space, I'm going to call this 1, 2, 3. But I'm going to go by ones on the y-axis. 1, 2, 3, 4, etc. So I'm doing this just to give myself a little bit more space. Okay. So what I'm going to do first is I'm just going to sketch the graph for x squared plus 1. And I'm just going to go ahead and plot all the points for all the integers, right? So my function here what I want to do is I want to figure out f of 0. I just want to get all the points. And I'm just going to plot all these points and sketch a graph. Okay, so f of 0, when I plug in 0 for x, I get 0 squared plus 1 is 1. F of 1 squared plus 1 is 2. F of 2 would be 5. And f of 3 would be 10. Okay, so those are the points on my graph. 0, 1, 1, 2, 2, 5, and 3, 10. So I'm going to go ahead and plot all those points. So 0, 1 would be right here. 1, 2 would be right here. 2, 5 would be right here. And 3, 10 would be all the way up here. Okay. And I'm just going to connect these. Right, we know it's a quadratic, so it's got some curve to it. And it looks something like that. And again, I want to approximate the area of the shape there. What is that area between the function, the red line, and the x-axis? So what it told me to do is to make 3 equal subdivisions. Now, it's pretty easy to see what the width of those 3 would be, but I want to show you a trick that can help you. To know how wide your subdivisions are, so subdivision width always equals b minus a over n. Okay? So I know my n is 3. My b and a are up here. This is a, this is b. So to figure out how wide each one needs to be, I do b, which is 3, minus a, which is 0, over 3. And I know that all my subdivisions are a width of 1. This can be a very helpful trick to make sure you get the right amount of subdivisions and they're the right width and they're all equal. So I'm going to go through and mark this thing off with my 3 subdivisions. Okay. So 1, 2, 3. Those are my 3 subdivisions. Okay. And I'm going to use those subdivisions here. I'm just going to turn these into rectangles to approximate how much area is beneath the curve here. Okay? Now the question is, should I draw these rectangles starting from the left, or should I draw them from the right? Well, we have to read the question again. I asked for a left Riemann sum. Right? I asked for a left Riemann sum. So, I'm going to use a different color. I'll use, I don't know, whatever color this is. For my first subdivision, the one right here, okay, I want to make a left Riemann sum. I want a left Riemann sum. And I want a left Riemann sum. Okay? So all I have to do now is find the area of those purple or blue or whatever the color is. The area of those 3 rectangles is going to be my guess, my approximation for this integral. So here's what I'm going to say. The integral from 0 to 3 of x squared plus 1 dx is going to approximately equal the area of these 3 rectangles. Okay? Well, let's take a look at the first rectangle. What is its base length? Now, looking at my graph, here's where you need to be careful. You might say, oh, that's 2, right? But remember, I skipped 1, so that base length is 1, and the height is 1. So the area of the first rectangle is 1 times 1. Plus, I need the area of the next rectangle. Well, its base is also 1, but its height now is 2. So it'll be 1 times 2. Plus the area of my last rectangle, that again has a base of 1, and its height now would be 5. Okay. So all I'm doing is calculating the area of those 3 rectangles. In fact, that first rectangle is actually a square, even though it doesn't look like it. Okay, so I have my approximately equal sign here. From then on out, I can use just a regular equal sign. So 1 times 1 is 1, 1 times 2 is 2, 1 times 5 is 5. I want to add those up. 1 plus 2 is 3, 3 plus 5 equals 8. Now again, do you think 8 is an under approximation or an over approximation? Well, 8 is definitely an under approximation, right? Because look at all the space I didn't count. Right? Take a look. There are just huge gaping white regions in there. But 8, following the directions, 8 is our approximation. We just know that that's really going to be too low of a number. Okay. So what I want you to do is now think about What if we did a right Riemann sum here? Well, if we did a right Riemann sum, I would have drawn my rectangles from the right. And it would have created an over approximation. I'm just going to write over this. You don't need to do this. I suggest you don't do this in your notes. But just take a look at what it would look like. If this was a right Riemann sum, my first rectangle would actually look like this. My second rectangle would look like this. And my third rectangle would look like this. Okay? Now just quickly seeing what that answer would be, this is an area of 2. This is an area of 5. And this is an area of 10. When I add those up, I get 17. So if I would have asked for a right Riemann sum with the same number of subdivisions, I would get 17. But that's too big, right? I'm counting this area, all these areas that aren't actually in there. So 17 is too big of a number. 8 is too small of a number. But what we did is we set a window. I know the answer is somewhere between 8 and 17. Maybe it's 13, maybe it's 14, right? In fact, we can just calculate it. Let me just look it up on my calculator to see what we get. Hopefully this loads quickly. So I'm going to figure out what the actual answer is, and it should be between the numbers 8 and 17. So I'm going to let my calculator do the work here. Eventually we'll be able to calculate this very easily. Okay? I'm just going to hit Math 9 to do an integral. I'm going to do the integral from 0 to 3 of the function x squared plus 1 dx. My actual answer is 12, right? Which is good because that's right in between the two numbers that we said, right? Somewhere between, we knew 8 was too small, we knew 17 was too big, 12 ended up being the actual answer. Okay? Now, we didn't get very close to 12 with either of those approximations, but we got decently close. Okay? We narrowed it down to something that's more manageable. Now, the question I have for you, the last question I'm going to leave you with for today, is how could I turn a Riemann sum, how could I make this Riemann sum be more accurate? Well, my left was too small, my right was too big, right? But I want it to be more accurate. Well, there's going to be a lot of ways that we can make it more accurate. But one way that we can make it more accurate is, what if we used more rectangles? What if I used 6 rectangles instead of 3? What would that look like? Let me just erase all this stuff. Okay, what if I had used 6 rectangles instead of 3? Well, let's think. Let's see what a left Riemann sum would look like. Well, using 6 instead of 3, it looks like it appears that I have less white space than I did when I used 3 rectangles. This is still going to be an under approximation, right? But I'm getting closer to a good one. But what if I used 12? Or what if I used 24? Or what if I used 1,000 rectangles? What if I used 1,000,000 rectangles? What am I going to say next? What if I used infinitely many rectangles? Right? The more rectangles I'm going to use, the more that white space is going to shrink. Right? That's going to be our key concept. We'll talk about this more later, but I just want to get your brains working on this. The more rectangles we use here, the more accurate we're going to get. And really what an integral is, a definite integral, is we're just using a Riemann sum, but we're using infinitely many rectangles. So that white space shrinks down to 0, which is pretty cool. I'll show you a graphic in class tomorrow that kind of shows how this works. That's it for today. We'll work on the kind of laborious task of doing these left Riemann sums from graphs. We'll work on that tomorrow. That's it for today. Have a great day. 2 chains, bye.